Yes, happy Wednesday. We're grading section 6.4. There's a bit of discrepancy as to the assignment. Here we go. Number 2, done. 4, done. 12 is 13. 54, not orthogonal because dot product is not 0. However, something real quick. Parallel, which would not be on a test or quiz. Parallel, to be parallel, one has to be a positive multiple of the other, meaning in order to be parallel, U has to equal 3V, 2V, 5V, 10V, 6V, positive constant times V. Now kiddos, if we did multiply V times 3, we would get a 3 and a 15, but what else would we get? A negative. So if we multiplied V times 3, if we were to do this, and if we were to do this and bring it in, the reason why these aren't parallel is because we should have a negative 315, which U is not. And since U doesn't have that negative, it's not parallel. It's not parallel. Alright, here we go. Number 76, for those of you guys that did the assignment you wrote down yesterday, this is what some of the kiddos are going to do tonight. Force due to gravity. They told you negative 5,400 and it was an up-down force. It was pulling down. The unit vector along the hill, you would have used a magnitude of 1 with cosine, a magnitude of 1 with sine. You could have used the projection in order to be able to solve using that formula to plug everything in. And then you would have found not only the magnitude of the force, which is right up here above, but you could have also found the force's magnitude of the force. There were 2 forces you were looking for, I apologize. The rolling down the hill one would be 93.7, and then the perpendicular to the hill one would be 5318. For those of you guys that wrote down the one from yesterday, excellent job getting it down, but let's go ahead and really quickly, can you guys star? Where's the homework sheet? Here it is. Those of you guys that wrote down the other homework assignment, can you just star these problems? That way you know which ones to worry or not worry about as far as the test. Can you star these problems? And if you didn't do them, you might want to go ahead and just write them in parentheses to peek at. So those of you guys that did not look at the website, you just got the old assignment from the end of notes yesterday. Let me go ahead and just get rid of this for now. Just say yes for save. Go ahead and star these ones because these are the particular ones I thought were most useful for the test. And if you notice, 76 is not on there. Yeah? 76 is not on there. Couple more seconds. Oh, thank you. Ricky, can you hit backspace? Alright, okay, so if you notice, 6.5 isn't very long. So let's go ahead and get back to notes. Let me wait to ask questions on 6.4 and 6.5 tomorrow when you guys have time to look at which problems are important from 6.4 and then the ones from 6.5. Sound good? Because we were a little bit confused. If you guys want to take a picture of this real fast, you most definitely can. That way you don't have to go look on the website tonight.
Are you going to change it?
No, this is the way it is. Sorry, the one on the website was always good. It was the other one that was old notes, I suppose. I need to remind myself to cross that. Okay, a couple more seconds. You guys got it?
Actually, Ricky, can you send that?
Alright, let's go ahead and go check out notes for 6.5 to finish this puppy up. You guys were writing these this morning, just a little bit ago. It sounds like it was a long time ago. Doesn't this morning sound like, I don't know, you were like getting ready for school? 7:10. I woke up at 5 o'clock.
Why? He wakes up
Decided to get a breakfast. Alright. Hopefully you guys got the formulas up above. The little question mark wasn't like, hey, who on earth is this? The little question mark is, this is who we had before for complex numbers, standard form. And now we're learning about trig form, which is our new one over here. Trig form, Z is just the name for the complex number, no big deal. The old standard form said A plus BI, we saw the real, we saw the imaginary. The trig form said, let me zoom in. Trig form says, we have an R, which stands for radius. kind of like magnitude. And you have cosine theta and I sine theta. So this little I, once again, not a vector, that's the actual imaginary number. But instead of writing the I after the B like we did before, because it made sense, we're writing the I before the sine theta, because if we wrote him after, it'd be confusing. Sine of theta I, sine of theta times I, sine of, So it's easier just to write the I before, that's why it's back there. Now, these examples down below tell us to take the complex number in whatever form it is and basically graph it and change it to be the other form. So all we're seeing is how to go back and forth. Okay? How would we graph number 13? You guys remember from yesterday? Did I graph the 1 on the x or on the y?
X.
X. Because if you need to write it down to help yourself remember, the x is the real, the y is the imaginary. You want to think about it that way. The x is the real, the y is the imaginary. Okay. So graph 1 on the x. And what do I graph on the y? Negative root 3, which would be a little bit before 2-ish, right? So we'll just put it there-ish. Negative root 3. Probably should be a little lower down, so that's okay. So go 1 to the right, go root 3 down, looking at our real and then imaginary components. The I, remember, that's just the imaginary number. Now, you have a picture of it. What quadrant is it in? I'm out of weight this morning, huh? Quadrant 4, yeah. Just a quick heads up, whenever we're trying to find R and theta, R is, I'm going to zoom in because it's a small picture. R is the length, remember? R is the length of the vector. Theta, even though usually we would probably go this way to save on time, theta for complex numbers always goes the positive direction. So to get into trig form, we want R and we want theta. Do you guys see it? We want R and we want theta. Let's go ahead and zoom out a bit. Let's keep solving. We need to get the trig form. Okay, if you guys look up above, is there a formula to find R?
No.
What?
Yes.
Yeah. And the formula for R is, hey, isn't that just the hypotenuse whenever you have the sides? And the hypotenuse, that can just be found with Pythagorean, or you can think back in vectors with the distance formula. A squared plus b squared, if we had components of a vector, x2 minus x1 squared plus y2 minus y1 squared, if we had the 2 points. And in this case, we can just do, since we do have it, we can just do a squared and b squared and not need to worry about the craziness of the distance formula. Mental math, what's 1 squared? 1. What's root 3 squared? Well, negative times negative is a positive. And root 3 squared is 3. What's the square root of 4? Okay. Because we are just looking, let's go back here real quick. Remember, for R, we're just taking the coefficients in standard form, so we're just taking the A and the B, not the I. You see it? You can kind of think of it in terms of, in trig form, we're going to have an I anyway, so we don't need to convert the I to I6. Okay, so we have R equals 2, and just to save on room, kiddos, because we're going to have to write that trig form, let's go ahead and just put the equals 2 right here. Okay. Now we also need theta. What's the formula for theta from up above? Inverse of b over a, right? So negative grad 3 over 1. If you guys want, you can go ahead and be using your calculators, because chapter 6 is definitely a calculator test. Have your calculators write out the formulas from what sections again?
3.
3, 4, and 5, right? 3, 4, and 5. Any formulas from 3, 4, and 5 you can write down on a card and bring to the test on Friday. If you don't bring it, oh man. Make a reminder, have a friend check on you, make sure that you have it when you come. But if you're not using your formulas, you can say, hey, it's a unit circle. If you're in your calculators in degree mode, you should get exactly what those of us that are trying to think of our unit circle should figure out. Negative 60 degrees. Or negative pi over 3. But what did I tell you about the angle and what it's supposed to be?
Supposed to be up on
The other way, yeah. It's supposed to be positive. So how do we take negative 60 and figure out what it would be the other way?
360 plus.
Exactly. You can add 360 if you want to think about it like that. And then we end up with beta is equal to 3. Okay? Beta is equal to 300. Or once again, just to save space, I keep on forgetting I have something else to write. Equals 300. Now guys, did the formula tell me this? Or did I have to look at the picture and figure it out? Okay, so pictures are important for section 6.5. Pictures are important whenever you do tangent inverse for vectors or for complex numbers. You gotta look at the picture to figure out what angle you're supposed to find. Now, we are supposed to write it in the trig form. Don't we have a trig form up above to plug into? Z is equal to, okay, check out the form. Let me zoom out a little bit so you can see. Plug it in, 2. R is 2. Cosine of who? 300. Plus I, sine of. Now you might ask, should I simplify?
No.
Let's talk about the next problem as to why you should not simplify. Let's talk about the next problem as to why you should not simplify. Trig form, I'm supposed to see it like this with cosines and sines. Let's look at the next example. So what if you're given something, a complex number? How can you tell? Because there's an I. What if you're given a complex number in trig form? How do you write it in standard form? Okay, we can make a graph first. How would we make a graph if we have it in trig form? Turn the angle 135. What quadrant would that be in? You guys see the 45 in the second quadrant? So turn 135. You end up in the second quadrant, right about there. Is that okay? There's our point. So we have a 135, and what else can we label? 5 is the length. So we have 5 as the R, we have 135 as the angle. In order to get it to standard form, I want to figure out who is A and who is B. Now Ricky's saying, wait a minute, that's a 5. Can't we just say it's a 3, 4, 5 triangle?
No, because we don't know that.
We don't know that this guy is 3 to make that guy 4. What if instead this guy was 1? Well, that would be root 24. There's a lot of different ways to get 5. Does that make sense? 3, 4, 5 is one option, but maybe not. How do we get it to be? Hey, what happens when you simplify? What if you just bring the 5 in, cosine of 135, plus 5 sine of 135. Wait a minute, where'd the I go? Don't worry. There he is. What am I showing you? Do you guys see the A and B yet? Isn't that going to just be A when we solve? And isn't that just going to be B when we solve? So it's actually kind of easy to go from trig form to A plus BI because all you got to do is simplify.
Since it's a 45-degree triangle, aren't both of them going to be the same? Because
Except second quadrant, which one's going to be negative? Cosine, good. So we're going to plug in root 2 over 2. You guys see me doing it over here, right? Exactly. So we're going to end up with negative 5 root 2 over 2 plus positive 5 root 2 over 2 times I. Dun, 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 dun. Got it. And technically, to make it all nice and snazzy, we would say something like Z equals. Z just is the name of a complex number. Just common notation. Z also stands for integers. So, going back real quick to up here, when you go to trig form, should you simplify? And the answer is no. Because when you simplify, what do you get?
Just gone right back.
You've gone right back to standard form. But the nice thing is, if you have trig form, just simplify and you get the standard form. But if you have standard form, you have to actually use your formulas in order to be able to get the trig form. I think standard form isn't that bad, just because he's kind of more what you guys are used to. You're not used to this whole r cosine theta plus I sine theta. And technically, if you get a little bit deeper into complex numbers, there is a shortcut way of writing this. Z equals r, we would say CIS theta. If you guys can imagine, it's r cis theta. CIS stands for cosine theta plus I sine theta. But we're not going to go into that much depth. It's totally fine for you guys just to use this form right here, all written out nice and pretty. Now you might be like, what on earth? Why are we taking what we already know how to do, and why are we figuring out another way to write it?
Because it's going to be on the test.
Well, it's going to be on the test, but also, in order to do math to complex numbers, we want it in trig form. It's a lot easier to do things to complex numbers in this form than in that form. And let me show you why. Hold on. There we go. To multiply and divide complex numbers, we have to have it in trig form. To multiply and divide complex numbers, we have to have it in trig form. Now, adding and subtracting complex numbers, we've already done that. Combine the A's, combine the B's, you're done. Combine like terms. But to multiply and divide complex numbers, we actually need it in trig form. And if we can get complex numbers in trig form, this is our given, we have them all nice and written in trig form, then there are formulas that we can use to multiply and divide. Nice thing is, we're in section 6.5, which means you can write these on your formula card, right?
Yeah.
Is there a pattern? Maybe I'm asking this too early. Think about it, don't answer. Is there a pattern to how the formulas work? I think so. Take a second as you're writing. I'm trying to think, is there a pattern to how the formulas work? Getting close to examples. But let me just for one moment zoom into the formula itself and just look. How do the R's behave? Just like the Z's. How do the R's behave? Just like the Z's. So if I'm multiplying two complex numbers, I multiply the R's. If I'm dividing two complex numbers, I divide their R's. And that is the new number in front. Multiplying the R's or dividing the R's. Is there a pattern to what happens to the thetas on the inside? Yeah. Yeah, they're being subtracted and added, and it's based on the multiplication or division. If it's multiplication, we add them. If it's division, we subtract them. Now, even though division is not subtraction, I think hopefully you guys can notice that you could correspond those two. And multiplication and addition, you can correspond those two, as opposed to if they were opposite. But otherwise, we just have the cosine of a new theta plus I sine of a new theta. Or cosine of a new theta plus I sine of a new theta. Let me zoom out. Let me have you guys get those two examples down. And as you guys get those two examples down, just to clarify just a little bit, just in case you can't see them, let me show you who is Z1. Oh, scroll up? Yeah. And who is Z2? You have to see the top.
Yeah.
Okay.
to get there with two multiplication solutions. You guys see the two complex numbers? They wrote them kind of funny. They didn't say z equals and z equals. They said, hey, this guy times that guy. Oh, alright. How to do first guy times second guy? Using the formula. We'll come back. The same thing down below. They didn't show z1, z2, but it is a complex number divided by another complex number. Did you get the top part, Lucy?
Yeah, thank you.
So once again, even though they didn't show it with z1 equals z2 equals, we're still doing the multiplication of two complex numbers and the division. Okay, so what's the pattern? To find the product of z1 times z2, we're going to have a number in front with a cosine of somebody plus I sine of somebody. Done. We got to fill in the blanks. What's the number in front going to be?
12.
12. How come? R times R, right? Look up above.
Oh, yeah.
Just take the r's and multiply. The formula actually looks more complicated than the actual solving is. Numbers on the outside, you just multiply. Now, hold on. I'm trying to show you guys the pattern to show you it's not as hard as it might seem. Down here, when we do z1 over z2, my 1 disappeared. We're going to have a number in front. I'm going to have cosine of plus I sine of. What's the number in front going to be for the bottom one?
One.
3.
Be careful. Division.
Oh.
What's the number in front going to be?
3. Oh,
3.
wait. Oh, 54.
Yeah. Looking at the two examples. I'm just setting it up.
I thought we did 145.
Oh,
So I'm just saying number in front follows the pattern. If it's multiplication, multiply the two numbers in front. If it's division, divide the two numbers in front. No big deal. No big deal. But the thetas behave differently. And technically the thetas follow exponent rules, which might not help you, but it might. When you multiply like bases, you add the exponents. The thetas seem to follow the exponent rules. When you divide like bases, you subtract the exponents. Anyway, coming on back. What are our two angles from number 45? One angle is pi over 4. Just take the angle. The other angle is pi over 12. Oh, we have to add those two? Yeah. Just get a common denominator, right? Can we just multiply by 3 over 3? 3 pi over 12 plus 1 pi over 12 is going to be? Which can reduce. That's our new one. Pi over 3 and pi over 3. Now at this point you can say, do I stop or do I keep going? You would think so, right? And you would get standard form, but maybe we should double check the directions real quick, and what do they say? Not to do that. So we'll just go ahead and box it and say, fine, whatever, that's what you want, done. But if we did want standard form, we would go the extra mile, we would go the extra step, and we would solve for 12 times cosine pi over 3 and 12 times sine pi over 3. Yeah. Oh, no, you'll do Okay. So cool, kids. What do we do on 54 then? If adding is what we do for multiplication, what do we do for division? Yeah, and subtracting, what are we subtracting? The angles. Just the angles, right? So angle 1 would be 4.3, angle 2 would be 2.1. So all we gotta do is just say, oh, sweet, subtract. 4.3, yeah, minus 2.1. It's already all nice and lined up. You guys remember the old way of subtraction? Hopefully. 2.2 and 2.2. Once again, leave it. Oh, not 2.5. I don't even know. There we go. They say leave it, so I say, okay, done. Now technically, addition and subtraction can be done in standard form, and technically, multiplication and division can be done in standard form. But if we did have yucky things like, let me add a page real fast, you guys don't have to write this. If we did have a complex number in standard form, do you guys remember how we would have to divide this? It was a long time ago. We would say, ew, we don't want that down there. Remember how? And actually, have to multiply by the conjugate in order to make things match, and then we would go ahead and simplify, and we would have to do all this math to get like this number on the bottom, and then this a plus bi up top. We can divide, it's just a mess. Multiplication would be a little bit easier, but we would get like I squareds that we would have to substitute and plug in for. So once again, we can do some of this in standard form. Let me actually do some of that. We can do some of this in standard form, but maybe trig form is easier, and we're about to get to stuff that trig form is the only way. Powers. For sake of time, let's not, hold on real fast. Let's not discover the formula. If we had time, we would discover the formula. If we had time, we would discover the formula. Instead of discovering the formula, let me just talk about if we need to raise a complex number to powers. How would you guys do if you had a plus bi squared? How would that go? How would you multiply? Would you rewrite it twice, or would you FOIL? Then you would get like an I squared. Oh, don't just be lazy. Come on. Rise above. Rise up. A plus bi times a plus bi. FOIL it out. You get an I squared. You have to plug in I squared. -1, right? Plug in, simplify. But as long as you didn't kill a puppy, go check out the rule again. You can't just bring it in. You gotta FOIL. Not too bad. But what if I started going here? Or here? Or here? You guys not feeling that?
Give up on life.
Right?
And
You'd have to rewrite it 3 times, or 8 times, or 24, and then, yeah, no. Now, there is something called the binomial theorem and Pascal's triangle, and that's really cool and all, but it'd still be quite a huge mess and take a lot of work. And yes, in Pascal's triangle comes the pattern of Sierpinski's triangle, which has been on my wall all year, which is the beginning of fractals, which allows computer animation to be what it is today.
we're not doing any of that.
New math that came in like the 60s.
When was the last time anyone did some stuff?
Probably fractals. As far as one that like affects your day-to-day life, as long as you watch movies, you don't watch movies. Or computer games, or video games. It actually came up because video game developers were trying to figure out. It was first talked about like the 60s. They started using it in like the 80s, 70s. Game developers were trying to figure out a way to make terrain look more realistically, more realistic, specifically mountains. And they couldn't get the program to show realistic mountains until one of the game developers remembered reading this math book that talked about fractals that this guy was talking about people were making fun of him for. And he was like, wait, hold on, this is useful. And all of a sudden, things became more realistic. Fractals. It's like trees and like how the tree branches, but it lets you find like the length of a coastline that's all jagged and impossible. It's all kinds of cool stuff. Yeah, cell phone, it's what allows you to have like tons of gigabytes on a little USB or like memory cards to be so tiny. It all has to do with fractals. Anyway, coming back. Topic for another day. I have a really cool like Nova video on it, but not for today. So most of you would fall asleep and be so sad. De Moivre's theorem. What? Yep. People in French, how would you say it? No. Who's in French? Come on.
Lucas.
No. Okay. He's too shy. Does De Moivre sound? De Moivre. Okay. Anyway, if we could be cool like him. I'm pretty sure he's French. Looks French. But long story short, what does it allow us to do to complex numbers without having to FOIL or multiply 3 or 4 or 5 or 24 times? Plug into a formula.
And,
But what form do we have to have it in?
the
Trig form.
yeah.
Now, do you guys see a z raised to a power?
Yes.
Right? There's a z, and where's his little power? So what we're really trying to find is z to the 4th. Okay, the arts and French numbers. That's like I say. Not this is 4th power, right? But guys, question, does our little trick of doing whatever the operation says to the outside still work? Yeah. Except instead of multiplying and dividing, what are we doing now? Taking the number on the outside and raising him to the power. But what do we do on the inside? Exactly. Doesn't that sound a whole lot easier than all the craziness I was just talking about as far as like foiling and having to multiply stuff out? Who wants to get this into standard form, which would be, hold on, cosine of 60 is 1/2, sine of 60 is root 3 over 2. 3 times 1/2 would be 3 pounds plus 3 root 3 over 2. We could have risen him to the 4th power, guys. You want to do that instead? Really, no reaction. You guys really want me to show doing that to the 4th power? And then
Yes,
see how you like it?
Do foil
Maybe I'll do it and have it ready for you tomorrow. But anyway, long story short, you have to foil it.
3 times.
Yeah, you have to foil 2, and then foil again. And simplify all your I squareds, I cubes, I to the 4ths. Let's just do the formula. So we have I sine of 4 times 60. We end up with, what's 3 to the 4th? Oh, come on, mental mathers. Isn't that just 9 times 9? 81.
So yeah.
Right? Cosine of
240.
plus I sine of,
240.
and with one quick plugging in, not having to do any foiling whatsoever, and if they wanted it in, oh, wait, do you guys see it? Caleb, now we're supposed to keep going. Standard form, we would just say no big dealio, because all we got to do is distribute 81. If we didn't know the cosine or the sine, we could just plug it into our calculators. But since 240 is in the unit circle, specifically 240 is 60 past 180, right? We could go ahead and be able to write 81 times negative 1/2 plus 81 times negative root 3 over 2. Which still isn't super pretty, but it's a whole lot faster than this 4th degree craziness up here. And we end up with negative 81 over 2, or 40.5, minus 81 root 3 over 2, 5. Dun, 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 dun. And I'm pretty sure getting from here to here would have been like a scary thing.
That doesn't matter, right?
Oh, you had Z from the beginning.
But like, is it okay that your answer is in Z to the 4th?
Yeah, because that's what they wanted you to find. They wanted you to find the 4th power of Z. See what I mean? We didn't add the 4th. Oh, okay. So this formula kind of saves us from a lot of crazy work as far as powers go. Is there any sort of funny powers that can show up? This will work for 2 and 3 and 4 and 10 and 12.
6.73.
850.
What about fractional powers?
Give up.
Wait a minute. Negative powers would be 1 over, so
No,
we
it
kind of
works
cheat and
the
just say
same.
1 over. But then we have to simplify. Maybe that won't be fun. You won't see negative powers. Good thing. But the crazy thing is, don't worry, we're just skipping here.
I'm not doing it in the mic.
If we're doing nth roots, stop judging. If we're doing nth roots,
I don't want the video.
wait, what does this look like? Huh? Is that Democritus? Lucas, I'm horrible. Anyway, it's like a soft touch.
I know.
This looks nothing like it. Although it kind of does. Now hold on, I need you guys to add something because there's something missing. I'm gonna go right here. Don't worry, I'll zoom out. To find the nth root, which is the same thing as z. I think I just like copied it wrong or something, like I cut it off. I did like this and then I didn't see it. Okay, you can see it multiple ways. If you have z to the power of 1 over n, which is the same thing as the nth root of z. Okay? To find z to the power, don't worry about the notes up above, just skip them. To find the nth root of z, or z to the 1 over n. Does the same pattern follow that whatever you do to the z, you do to the r?
Yes.
Okay, that's not bad. But what on earth is going on over there?
A mess.
That's
Wait. If you were to multiply the theta by the power, wouldn't you be multiplying by 1 over n? And wouldn't 1 over n end up dividing n? But what's weird is this whole 2 pi k thing going on. Or if you're in degree mode, it would be 360k. The long story short, whenever you cut down angles, and if you guys are trying to track with what's going on, when we have trig form, we're trying to find the angles that work between 0 and 2 pi, 0 and 360. And so far, if we raise an angle to a power, a complex number to a power, if we multiply an angle, a 60 will become a 240, a 90 will become a 180, etc. If the angles get bigger, then there's not going to be any more options, because if they get bigger, only one's still going to fit between 0 and 360. But as soon as we start cutting them down, which is what we're going to have to do for nth roots, we have to include more angles, more options. And if some of you are thinking back to like the cosine 2x, sine of 2x, cosine 4x, sine of 4x that we were solving in chapter 5, there were more answers than anticipated because when you cut down the angles, more were able to fit. Now, I'm not going to go too crazy with this because I can tell you right now, if there is one of these on the test, there will only be one of them. If there is one of the nth roots on the test, there will only be one of them. But the long story short of it is, when you go to plug in, when you go to solve, you're going to find n answers. Yeah. You're going to find n answers. Okay, let me show you where we are. There was one example that we didn't get to do, or one set of examples, and then we're done. Now don't look at that one, look at the one online. Remember, the one online was a lot shorter. This was from an old year when we had more time. What I'm going to do is, when I save the notes online today, I'm going to make sure to work out these examples for you guys to check out. Okay? I'm going to work out these examples for you guys to check out. When you get your homework, go look at the notes. Bye, cool kids. I'll see you tomorrow. Yeah, go ahead and staple it for me, Austin.